a nice occasion. So it's a pleasure to be back in Russia. I was here for the first time in my life in 1972 in Moscow, then again in 87, and so this and a number of years around that time. It's also a bit sad because I noticed that while I'm getting older, Moscow seems to be getting younger. So sort of mismatch, but okay. It's also very nice to see a lot of colleagues, Russian colleagues that I've been in touch with in recent years. Normally I meet them outside of Russia, in Holland or Japan or places like that, but very nice to see them, and I hope to talk to a lot of people this week. Then finally, yeah, Jacek said it, Studia Logica. Of course, we owe so much to the Polish logicians and to the interface that they created between East and West in the time that was difficult. Maybe one more point. So I saw already next time you're going to the Ukraine, but Ferrong says that we should also do the Beijing thing. And one thing about the Chinese versions and the many people, of course, they are mainly there for the group picture. The Chinese conferences have this huge group picture where you see everybody arranged, carefully arranged in order of hierarchy. So you can figure out how important you are by where you are exactly on the picture. But maybe we could also do a group picture this time, because initially people laughed about the group pictures, but I find that as I'm getting older, it's my only means of remembering what happened in the past. So I spent many hours looking at this person and that person, so it's part of your memory. All right, so I'd like to talk about today about dependence. So dependence is a very general topic. Many logicians have already looked at it, so I could easily enumerate about seven different approaches to the logic of dependence done in various different countries. But Alexander Baltag and I think that we still have something to say, so, and you'll see what that is. In this talk, I'll explain the main ideas. I'll mention the results. I won't have time to really go into proofs, but there is a paper, and if you're interested, I could send you, we have lots of details. So let's start with the talk. So dependence is a ubiquitous notion. So we can talk about dependence of a variable x on a variable y, or maybe of a variable x on a set y. And it occurs in lots of areas of science, mathematics, even daily life. So probability, construction, I'll get back to that later, in vector spaces. But also in social life, we talk about dependent occurrence or behavior. For instance, I think when we think in terms of causality for behavior or games. Now, the fact that something happens a lot, you see that notion a lot, doesn't mean that it's one single notion. So, in fact, we'll get back to that as well. So there's great diversity to sense of dependence. Even inside logic, logicians also use the term dependence, but it isn't even clear that logicians mean the same thing when they use it. To take an example, in a quantifier combination, like for all x there exists y, rxy, logicians like to say that the truth of that has to do with the fact of choosing y dependently on x. So that's a sort of dependence which you could exemplify in a scaling function. But logicians would also say that a set like this is actually dependent or not independent, right? So if these were two axioms, it would be a particularly bad axiom set because the phi is redundant. In fact, I think in the most recent issue of the journal Philosophical Logic, which to my great surprise was not on your list of most highly widest impact papers, so much for these lists. There's a 50-page article on dependence by Lloyd Humberstone. Well, that's actually about this notion of dependence, so dependent sets of axioms, premises, and so on. Let me also make a very rough distinction. Some forms of dependence are ontic, so they are about coupled behavior in the physical world. So, for instance, if I hold my hand like this, then this hand has become dependent on this hand. Right? It's got to move along if I move this hand. So that happens in the real world, but a lot of senses of dependence aren't ontic, they're epistemic. So they have to do with the fact that learning something about one variable tells you something about another variable. We will explore one basic sense of dependence that hopefully applies widely. So let me go straight away to a simple example. you might think of a database, or just look at this table. So we have three variables, x, y, and z. And what I've done is there's three tuples which indicate the values that these variables can take. Right? So you see three lines, 0, 1, 0, 1, 1, 0, 2, 0, 0. That's all. Now, intuitively, I might say that y variable, in this table, y depends on x. What do I mean by that? Well, if I fix the value of x, the value of y is also fixed. I'll make that more precise on the next slide. Of course, that's relatively easy to do because fixing the value of x just means moving to one particular line. And you will see one value for y there. So definitely y depends on x. But what's also true is that z depends on y. Because if I fix the value of y, for instance, if I fix it to be 1, that happens in the first and the second line, then the value of z is the same. And of course, I could also fix the value of y to be 0. Well, just z has its value. So y depends on x, z depends on y. And by transitivity, z depends on x. It's not the case, if you look conversely, that x depends on y, because, for instance, if I fix the value of y to be 1, x can still vary. Right? Look at your first and second lines. So the dependence doesn't work the other way around. And it's also not true that y depends on z. I leave that to you, but it's easy to see. So, if you wanted to think of the dependence structure in my example, what you would actually see is a sort of graph of variables. And in this case, it will be a linear order, from x to y to z and nothing. Now comes an important point. Many logics of dependence that are around nowadays use this notion of dependence, but actually our starting point is different because call this global dependence. However, there's another simpler sort of dependence, which you might call local dependence, which actually says that a variable depends on another just at some particular position. So for instance, if you look at 2, 0, 0, I might say that x depends on y there, because if I fix the value of y to be its value at 2, 0, 0, which equals 0, then in fact it's fixed what the x is, it's 2. Now my example is a bit simple. You might want to see a few more lines to see how this works, but basically, you know, I could do that, use more space, but this is the main idea. So, and in fact, the global dependence, in a sense, is just the universal form of local dependence. You're globally, so y globally depends on x if y depends on x locally everywhere. And that's basically a very simple fact, often overlooked. So the basis for the logic we're going to do is going to be local dependence. That saves us a lot of complications. Okay, so much for this. Actually, I once gave this talk with my younger son present, who's more in applied mathematics. He said this was the last slide he could understand. So the rest is going to be logic. Okay. Well, if you want to turn what I just said into more general models, you could work with dependence models. So there are tuples. Basically, there's a set of variables. Although it doesn't really matter that they're variables, they're just any objects that could serve as variables. They could be headings in a database or anything else. There's a set O of possible values of the variables, so also just any object. But now comes an important point. There's a family of functions from the variables to the objects, but this family does not need to be the full function space of all functions from V to O. And this is crucial. It's also crucial to my earlier example. Gaps in the full function space are exactly what dependence is about. If you have a full function space, then any variable can change its value without any side effects on other variables. Then there is no dependence. But if there are gaps, if certain functions are missing, then you get the dependencies that I talked about. So as a slogan, remember that gaps is dependence. That's also true in my example, right? If you think about positions that my hands can occupy in space, then this dependence has to do with the fact that it's not all functions from spatial locations to where my hands are, right? That's gaps. Okay, a few definitions. Local dependence of y on x. What that means is, so take an s, a function. If for all functions that agree with s on x, that's what that notation says, then they also agree on y. Global dependence, that same thing, but for all functions. Right? That's the point I made earlier. So I start with the local dependence, local in s, and global dependence is here. And here's a few more notations that are all rather obvious. So, dependence models. Gaps in the function space is dependence. Few simple definitions. What these apples mean, not for you but for me, it says Johan rushed through this slide. So, there's actually lots of interpretations of these abstract models. I already said that dependence is a very a general notion. So you can think of dependence in terms of information, as I said. You can actually also, a popular interpretation is interrogative. That dependence has something to do with answers to questions, so that the notion of dependence actually runs between questions. Dependence happens in dynamical systems. Then you think of these functions as global states of the system, and the dependencies arise because the system cannot take its states in the full function space, but only in a part. And I hope to get to the example of games. So it's an abstract notion, but widely occurring. Maybe a small thing. The notion of dependence I've defined for you is semantic. What I just did, semantic. But you might think that there's another very broad intuition of dependence, namely that one thing depends on another if it can be constructed from it. So another general intuition of dependence is construction. Y depends on a set of objects x if it can be defined from the x. Because then in some sense, if you give the values of the x's, the y has to come along, right? Since it's a function value over those objects. So for instance, if we have those functions, then indeed we will have, so that's my first fact, functional definability implies semantic dependence, because what you're going to have is that for all of these functions s, the value on y is going to be, well, some sort of c involving these functions on the values for the x's. But it's also easy to see that conversely, if you have semantic dependencies in my sense, there's going to be an algebra of functions that actually witness them in just this way. Well, just think of the way mathematicians talk. When a mathematician says that a function is well defined, what he actually says is that if you have equality for the arguments, you have equality for the values. Once you have that, you're entitled to giving a function definition. So thinking as a mathematician also works the other way around. It's actually an algebra of partial functions if you think about it a bit. But these two perspectives are actually related. I'll continue with the semantic view. The definability view will come back a bit later. Okay, take a breath. What are the general abstract properties of dependence? Well, here they are. You have reflexivity, so a variable depends on any set that it belongs to. There's monotonicity. If a variable depends on a set, then you make the set larger. It also depends on the larger set. This all follows immediately from our definitions. And we have transitivity. So if a set of variables y depends on the x, and the set of variables z depends on the y's, then actually z depends on the x's. Reflexivity, monotonicity, transitivity. This is about the level of analyzing dependence that was already made by Armstrong. I believe that's in the 1910s, or maybe even earlier, famous paper by a mathematician on abstract properties of dependence. Here's a theorem for you. Think abstractly. Think of any relation D between objects and sets of objects that satisfies these three properties. So any relation D that's reflexive, monotonic, and transitive is isomorphic to the dependence relation of some dependence model. This is a representation theorem. What it says is any abstract relation can be regarded as coming from these properties from a dependence model. I said I was not going to go into proofs, so I'll just leave some of you who think very fast, let's say like members of the Russian Academy of Sciences, to think for 2 seconds and see that this proof is correct. Then I'll continue. But it's actually a fun proof. So that was, I think, enough, more than 2 seconds. In any case, it's easy to prove for yourself once you have the result. But what I want to stress, maybe more for the philosophers, is actually an interesting point, which is both technical and conceptual. Because you might think, but this is very strange. Johan has got everything mixed up. Why is this? Reflexivity, transitivity, and monotonicity, we already know, are the characteristic properties of a famous logical notion, but it's not dependence, it's classical consequence. Like in Scott's famous paper on consequence relations in 71 or something like that. How can that be? How can it be that what's characteristic? Because consequence, notice, is not the same as dependence, right? Consequence just says that if the truth values of the premises are all one, that the truth value of the... So if you wish, consequence is a very poor sort of dependence. It says that one particular combination of values for the premises forces some particular value for the conclusion. But it doesn't talk about the other combinations. So it's less rich than this. Okay. Well, actually, you could think, in that sense, dependence is more like consequence between questions. Actually, also started in Poland, right, by various Polish logicians, Ardukiewicz, among others. Dependence between questions means that any combination of truth value answers to the premises forces a particular truth value for the conclusion, whether true or false. That's actually much, that's dependence between questions. Well, well, of course, there's nothing wrong in what I said. What actually turns out to be the case is this. It has something to do with the structures that you work with. So, with two objects, so it has something to do with how you represent certain graphs. For instance, I mentioned that in my first example, there was a three-element graph, x to y to z, which could be represented in dependence by that table. Now, if you remember in my table, I don't know how to go back on the slide, so I'll just say it. I used the variables x, y, and z, and I used 3 values, 0, 1, and 2. It's easy to see, I'll just claim that it's impossible to represent the line with 3 points in a dependence model with only 2 objects. That's just impossible. You can look at my graph, and at my table, and you can see that. But in consequence, you can. If you just think in propositional logic, it's easy to have 3 formulas where one implies the other implies the other, and nothing the other way around. So in fact, there's a sort of interesting question here. If you analyze the notion of dependence, it's going to behave differently from consequence if you restrict the numbers of values. So one open problem is find the structural properties of dependence for finite sizes of the object. Another thing that's interesting, again speaking to more the philosophers, is that there is then a certain analogy, not quite, but this identity, but analogy between dependence and consequence. And since logicians are, of course, also very much into non-classical notions of consequence, that would raise the question, what are non-classical notions of dependence? I won't pursue that, but I think that's a whole line of, interesting line of questioning that you can go into. Now I want to explain a bit of background to the approach that I want to explain. And this actually goes back to work in the mid-90s I did with Andrei Kandlemety. So, CRS-style first-order logic, never mind what CRS is, it's a term from algebraic logic. CRS was motivated by actually the following question. Why is first-order logic undecidable? Of course, most of you just think it is, and you accept that, because you probably have a gloomy view of life. So you think bad news, well, all of life is bad news, ending in the worst news of all, so to speak, so we'll just accept that. But you could ask the question, first, what is it about the structure of first-order logic that explains why it's undecidable, where the undecidability actually says that it has a certain mathematical richness? Okay, that's usually the source of undecidability. For that, you need to go back to Tarski semantics and ask yourself, what is Tarski semantics supposed to do? Well, what it's supposed to do is to give a compositional semantics for the first-order language. That's, of course, Tarski's famous use of assignments to get this recursion going for the formulas. But is that in its, and then it seems you get the standard semantics, but the question, and if you have the standard semantics, you have standard validity, you have undecidability, but is there maybe some point where we can break this? Now, CRS-style first-order logic breaks this as follows by saying, we'll keep Tarski's idea, we'll do the compositional semantics, but we identify one feature in the usual notion of validity, which is actually higher order, and which explains the complexity of the validities of first-order logic. And which feature is that? It's the fact that we assume that we're working on a universe of all functions from variables to objects. It's a gap-free, complete function space. And once you start thinking about that, in the core of the arguments for the undecidability of first-order logic, that fact is used, even though it's seldom highlighted. So it's a natural question to ask yourself, and what does that express? What that expresses is that standard semantics for first-order logic makes the following assumption. All variables are completely independent. They can change their values regardless of what the others do. That's an assumption, I would say, not a, it's a very strong assumption. If we drop that assumption, we need gaps. So we'll use models, first-order models, but this time there's only a set of available assignments. So think of my dependence models. And we'll now interpret the existential quantifier as saying that MS satisfies the exists x phi if there exists an object, another assignment actually, such that S stands in this relation to T, and phi is the case. This is just the standard clause for the existential quantifier. With this modification, that this T has to exist in the set of available assignments. Right? So you just don't say any T, no, it has to be in the set of available assignments. Where, of course, in first-order logic, notice that this time the index X has gone to become a superscript because the relevant connection between S and T here is not that they agree on the value for X, they agree on everything else. But I guess most of you are logicians, that's about the same. It's very different, but it's about the same, technically. Okay. What that does is, here's a fact. In the earliest version for that is in a paper by Nemeti from 1985, but we had other versions and much different proofs at the time. The first-order validity on generalized assignment models are recursively axiomatizable and decidable. Think of that, that's the decidable heart of first-order logic. Which things lead to undecidability? Well, actually, some of the things that look the most harmless. Take, for instance, a formula like there exists X, there exists Y, phi, implies the opposite order. This is so boring you wouldn't even give it to a student, but actually, mathematically, it's very strong because this is a typical independence property. It says that it doesn't matter in which order I introduce the variable, the object. It's very strong. Or for those of you who know something about undecidability proofs, if you have something like that, you get confluence in the structure that you're working on, and once you have confluence, you can encode tiling problems and get into high complexity. Okay, so that's the background. But CRS is not yet a dependence law, because the dependence was only mentioned implicitly. So basically, the way I described it at the time was, CRS is the decidable sublogic of first-order logic, which you get if you allow dependence in your models, because these generalized assignment models are dependence models in our terms. But that was all. We didn't introduce dependence explicitly into the language. So let me now do that. So here's the logic of functional dependence. And so we have atomic formulas, Q of X. We have dependence atoms, dxy. We have the usual booleans. And we have something that you could see as a sort of dual of the first-order quantifier or a modality. In fact, quantifiers and modalities are about the same, at least if you live in Amsterdam. But I hope that most logicians are able to think in these two ways. So the models are, for this language, are dependence models. There's a valuation which maps predicates into the given predicates on the objects. And here's your truth definition. So the clause for the atomic predicates is as usual. The dependence atoms are interpreted locally in terms of this notion I've already given you on my second slide. right? So what this just says is that locally in S, so given the value that S gives to the axis, Y is determined. And here is my interpretation for the main operator. What it actually says is that dx phi means that in some sense the values of the axis fix the truth value of phi, or to be more precise, for every assignment which you have in the dependence model which agrees with S on all the x variables, phi is the case. Even this you could see as a form of dependence, because if you think of phi as a Boolean variable, right, so it can just take two values, 0 or false, then actually there's a form of dependence here, but just read it like this. As I said, you could think of this as a dual of the first order quantifier, because the first order quantifier would have the x not as a subscript, but as a superscript. But one way of doing that is to say that the first order quantifier you get by taking d over all the variables minus x. Okay. So that's the semantics. And our basic notion is local at some assignment. The expressive power of this logic. Well, first, actually, there's two things that people say when they think about the semantic dependence. What I've said is that fixing the value for x fixes the value for y. But many people talk differently. They say you have dependence when changing the value of x implies changing the value of y. In fact, with this example, I was actually doing that because I was changing the value of my upper hand. And the other one had to come along. But actually that's in our system, because if changing x implies changing y, then keeping y the same implies keeping x the same. In other words, this is just the converse. Right, so it's all set aligned. The global sense are included. If I have dependence, but I take the empty set of variables, then I'm quantifying over all states. Right? Since all states agree on the empty set of variables, therefore the empty set phi is the universal modality, and that means that the system can define the global dependence notion just as the universal modality over the local one. And there's various other things that we can do. Question for Valentin, what's the notion of bisimulation? I just wanted to give one talk where I don't present the notion of bisimulation. And I thought I managed to do it. Right? This is all I'll say about it. And actually one reason why that's not a completely obvious question is there's a lot of structure in the dependence models. You really have to think a bit about where you would want to do the simulation. This, maybe I'm even going to skip this. Maybe it's not so important. But there is one difference if you work with these modalities or quantifiers compared with the first order quantifiers. What you're used to in first order logic is that if you have a formula and you look at its free variables, those free variables determine the truth value. If you have two assignments in your model and they agree on the free variables, then the formula has the same truth value. That works differently here because of this duality. So this slide just gives you the important variables in a formula that determine its truth value. They're called the fixing variables. They can be defined recursively. They give you the same behavior as the free variable, but they're not the free variables. I'll just say that, so be warned. Okay, that takes a little bit of adjustment, but it can be done. I think this I'm going to skip. So now you have LFD. So think of LFD as a sort of version of first order logic over dependence models, but we've now introduced explicit local dependence atoms. Okay, so it's in the language. And we can now see this as a sort of the core logic, in fact, a decidable core logic of dependence. Before I say more about this, let me also point out that I could look at this same situation also from a modal logic point of view. This is a bit of difficulty, so Alexander and I have been going back and forth on this. Because our feeling is, if we present LFD as a modal logic, half of the referees are going to like it, and the other halves won't. So then we decided we'll present it as a first order logic, but then we lose the modal referees, and eventually our compromise in the paper is that everything is done in parallel. right? So we give proofs and notions both in modal style and first order style, where, of course, again, I notice that if you live in Amsterdam, you will, so if you were a referee from Amsterdam, you would say the paper is redundant, because basically it says the very same thing twice. Okay, all right. But how could you think of these models I just gave you in terms of modal logic? Well, think of them just as relational models. And there's actually an interesting abstract point behind their conceptual point. In some sense, for many things you want to do with the language, the objects don't matter so much. So for instance, I could also think that the models I just gave you just look like this. They're a set of states. There are these important relations, squiggle X, and there's a valuation. These squiggle X are equivalence relations, and there's a few conditions they have to satisfy. Now we're in modal logic, right? So I no longer have objects. I just regard these functions as the states. But I don't look deeper than that. The only thing I need to have is these relations. And then standard relational models are relational models which satisfy one additional condition. I see. I forgot an intersection. So the relation for a set X will be the intersection of the relations for the set members. This is just an abstract modal point of view on the dependence models. Now many notions for modal logic make sense. I say by simulation, but Valentin still has to define it for us. Filtration and much more. Now here are two key theorems in our paper, and the proof is far too long to say something about it. The first is, the modal viewpoint is closely connected to the original viewpoint I gave you as follows. Each standard relational model, where this squiggle X is the intersection of the squiggle X for the members, is isomorphic with the dependence model and vice versa. So that's the same thing. And the second thing, that's the hardest, is each general relation model is a p-morphic image of a standard relational model. This is actually harder to prove, takes a few pages, but that's very useful to know. So the modal perspective and the one I gave before are really close. This I'm going to skip. So the perspective presented here, then modal and first order are two sides of the same coin. Notions and techniques apply either way. Let's see. Now I like to do a little excursion with what I consider the attractions of this thinking in tandem. And actually I'll do it from modal logic to the first order view of the system. So, because I thought you might find that of some interest also independently. For instance, take a typical modal method like filtration. So filtration is a method by which you prove decidability of various modal logics. And it's usually considered a method that's very typical for modal logic. And okay. But I want to show you how you could also, in our context, think about it as something that applies to first order logic. And I'll do that in the setting of proving the decidability of LFD. So LFD is decidable. That's just one of our main results. Okay. So let's view LFD as a first order logic. But in fact, let's just start from any model for first order logic and think of it like this. So first, consider a finite set of formulas. Add all atoms d, x, y, where the variables in the x and y occur in these formulas f. Close under single negations. Call the resulting finite set boldface f. Now, scratch the word modal there, that I should have. So given a dependence model M and an assignment S, the f-type of S and M is just a set of formulas in your finite set which are true. This is standard terminology from model theory. So each S in your first order model has a type. It's just a finite set of formulas, namely the ones that are true from there. The induced type model of your model M consists of all such types. So what is it? Well, it is a finite family of finite sets. You could think of it as a very rough approximation of your given first order model, because it's only a finite structure. And in particular, what it has dropped is you get information about formulas that are true. You don't get information anymore about the objects. because the objects from the original model don't occur in this construction. You might think this is a disadvantage, but actually I have Stanford students now, the winds of metaphysics are changing, who actually object to model theory because it talks about objects. So they think this is a very bad thing. And instead, they want to have a semantics which is object-free. So these models are actually have done away with these evil objects that are underneath and that actually have these properties and so on. Okay. Now, considering a induced type model, type M, for any first-order model, it's easy to see that these types satisfy the following properties for all relevant formulas. A and B are the usual clauses for a maximally consistent set. C is very mild, yeah, okay, not even important. What's important is the witness clause D. So if this is the existential modality for the D, so what it says in the model is that there is some T which agrees with S on the X values, where phi is the case. Well, then there is a type, of course, for the witness type for the phi. And what it has is actually these properties that I give here. So phi is in it, and they stand in a particular syntactic relationship for which, at the moment, let me just say it involves these fixing variables I talked about earlier. So these are technical details of the system that maybe don't matter here. Now, if I just make these things part of a definition, I could define an F-type structure as a finite family of F-types which satisfies these conditions. Okay. And now what we can show is that each F-type structure is induced by a dependence model. This is a long proof. Again, it's in the paper. I'm not going to go through it. It's actually done via a technique that I also used with Andrej Nemeti to prove the decidability of the guarded fragment, for those of you who know. So it's actually a sort of extension of the decidability proof for the guarded fragment to deal with dependence atoms. But the fact is just that F-type structures of the sort I gave are induced by dependence models. So therefore, LFD must be decidable. Why? Well, by the preceding results, being satisfiable in some dependence model is equivalent to occurring in some set in a finite type structure, because that's an if and only if. If you have a model, there is a type structure that you belong to, but my representation theorem says that if you belong to some set in a type structure, you would also be satisfiable in the dependence model, and it's clearly decidable whether a given modal formula occurs in some set in a finite type structure. What this leaves open is whether LFD has the finite model property. Because our representation argument actually creates an infinite dependence model for a finite type structure. Well, those of you who are into this business of filtration will know this sort of issue. Open. Of course, if you're one of these philosophers who don't believe in objects anymore, then this is a completely uninteresting question. Because the finite model property asks, is there an object with real objects in it? Sorry, is there a finite model with real objects in it which does it? But that's precisely what you reject. Okay? So that's good, because if you have that philosophy, there's fewer mathematical problems to worry about. Like this one. But normally you'd worry. Also, another open problem, what's the computational complexity? We don't know. Maybe interesting question. I said it also applies to first order logic. So I could do the same for first order logic. I take an arbitrary first order formula which is true somewhere, I create the type structure and so on, and I just check whether it occurs in some set in some type structure. But of course the fact is that FOL is undecidable. Now, what is decidable is whether any given first-order formula has a finite type structure. What's also true is that each type structure is representable as a generalized first-order model. That leaves us only one possible conclusion, which I personally found very surprising. It is undecidable if a given type structure is representable as a standard full first-order model. I mean, all of them are representable as dependence models in my generalized sense. This question has got to be undecidable. Because if this were decidable too, then I'd have a decidability argument for FOL. You don't look particularly enthusiastic. I actually found this surprising and interesting that this is so hard. Now, proof system. Those I'm just going to show. There's also a completeness theorem for LFD. So here are the principles of LFD for this decidable logic. So S5 for each separate dx, monotonicity, the basic structural properties in C, which I mentioned, and maybe I'll just mention this guy, the transfer action. It's really simple. So what it says is, if all the variables in capital Y depends on those in X, and if phi depends on Y, then phi depends on X. That's, I hope you can see that that's reasonable. The proof calculus is sound. Here are some examples of derivations, which I'm going to skip. We also have a completeness theorem, so the axiomatic proof calculus for LFD is complete. I'm not even going to go into the proof, but basically, if you've understood the decidability proof, it's really easy to turn that into a completeness proof. Then, for those of you who don't like Hilbert-style axiom systems, which is a lot of logicians nowadays, here's a Gensen calculus for LFD. Okay. Again, I don't expect you to take this in, but there is. So there's also a sequent calculus system for LFD, which you could use instead. And the sequent calculus for LFD, well, it doesn't have cut elimination exactly. It's up to the atomic dependence axioms. But basically, the sequent calculus and the axiomatic system for LFD have the same deductive power. This may also be useful because for some properties that are open, we have found it very difficult to prove interpolation, for instance, for LFD. But we've worked with the Hilbert-style calculus. And what we're thinking at the moment is it might actually be easier to use our Gensen calculus, but we haven't yet done it yet. Then again, a topic that will be familiar for modal logic. So the base logic, LFD, for functional dependence is decidable. But of course, you could add axioms and ask yourself, what do they do? Well, for instance, if in our logic you do something similar, like what I said about first-order logic, you add commutation axioms for the D modalities, then again you impose a form of independence, and in fact the logic of commuting dx dy with that thing is undecidable. Okay, that's the base system. I'll use the rest of my time so I'll summarize where we are, and now I want to go into, I'll say what I want to go into. So, I said, dependence is a very general notion, and what I've basically done for you is define one very general semantic intuition. Dependence as determination. Fix the values of the x's, you fix the value of some other variable. That was the semantic view. For that notion to be interesting, it's important that you don't work with full function spaces, but with models that have gaps. So gaps are good, right? This is, of course, the same in life, right? If you think about a meaningful relationship with a person, it means that there are gaps in the function space from the location of that person, functions that map that person to some place on the planet, right? It's like this. So gaps are good. Okay, good. You get that point. Then, are bad. Yeah, are bad. Yes. Now, okay, that was the first thing. Then I said, you can study this notion of dependence in itself, abstractly. Then you get a number of properties which actually suggest that dependence is a sort of generalization of the notion of consequence. That's interesting because it suggests all sorts of analogies you could develop between the study of dependence and between various sorts of consequence relations. Then what I proposed was LFD as an example of what may arguably be the core logic of functional dependence. It's a small, decidable system. It's relatively perspicuous if you take a little time to read our paper. So, and you will see that whether you're a standard logician or a modal logician, you can understand it because it actually has both these features combined. And so it's decidable, there's a completeness theorem for it, although there's also a lot of things we don't know. Now, what I'd like to do now is end with two things, because this is just a sort of base system. And the question is, how far does this go? And I'll look at two things. One is some extensions of the language of LFD to see what happens, right? If we give ourselves more power to talk about dependence. And the other is, and that will be, to me, the most intriguing topic at the moment, to now go out into the world and analyze real notions of dependence as you find them in mathematics, computer science, and so on, and see what they have over and above my core logic. But let me first talk about language extensions. Simple extensions are just things like you could add function terms to the language and so on. That's relatively simple. It also makes sense to add term identity, but then I have to confess we have a problem. At the moment, we know that this is recursively axiomatizable, but if I add identity between values, actually it's open to us whether that's decidable or not. In fact, Alexandru proved 2 years ago that it was decidable. This got published in Advances in Modal Logic. The proof is wrong. I leave it for you to draw your conclusions about the quality of refereeing for advances in modal logic. But actually, maybe a more interesting question is this. What about independence? Because many people think that's about the same. Either you start analyzing dependence or you start analyzing independence. But let me notice that independence is not the same as the negation of my dependence. If I negate dxy, I'm only saying that it's not always the case that the x values fix the y values. That's rather weak. A natural sense of independence of y from x would be that if you fix the values of x, it does nothing to the values that y could take. So fixing the values of x leaves y free to take on any value it can take in the model. Or if you want to think epistemically, knowing the values of x doesn't tell you anything about the possible values of y. That's one. I hope you see that. This can be formalized, what I said here. I don't do it on the slide, but I can give this a completely clear technical meaning. And what I then get is an independence modality, which actually says that IXY says that if in the model I fix the model to be all the values of x to be the same, then the range of values I'm going to see for y is the same as the range I would see in the whole model. And now comes the point. The modal or first order logic of independence is undecidable. Okay. And why is this? Maybe just one small thing. We know that's a result by Tarski. The three variable fragment of first order logic is undecidable. And actually, we can embed the three variable fragment of FOL into this modal logic, because what I just do is I put enough independence statements on x, y, and z to force the fact that x, y, and z form the full Cartesian product. This is easy to do with the meaning I just gave. So by just putting some a suitable number of these independent statements, I can actually force the model to look, at least for its x, y, z part, as a full Cartesian product, and that does the embedding. Okay. Some of you may be a bit puzzled because you may have read somewhere that independence and dependence is about the same, because say Hintika started his analysis of IF logic with independence, Venen starts with dependence, but in terms of complexity, it comes out to about the same thing, second order logic. That's compatible with what I say. The point is, if you develop these systems on a second order basis, then you won't see any further difference. But if you go on a very weak basis, like what I've done here, then you will see this difference. Right, so this is... yeah, so independence is really harder. For those of you who've been to the SD summer school, there is of course a dynamic logic perspective on these things that would have to do with changing dependence models. But just as I promised myself not to talk about bisimulation, define bisimulation here, I thought I also wanted to show you that I can give at least one talk which doesn't talk about dynamic epistemic logic. So I move on. I've mentioned it, but I won't get into this issue, even though there's lots of issues here. Then the last thing at this level, and now we already get to There is a sort of question in our mind whether the system LFD, which I've given you, is exactly the right setting. And this is because at the moment, Amsterdam is taken by a topological storm, so to speak. Everything has to be topology. It's a bit interesting cultural question why this is the case. Part has to do with appointing Nick Beshenishvili, so then you get this Georgian influence, and then before you know it, everything has to be topological, Esakia, and so on. It also comes from across the Atlantic in Pittsburgh and learning theory and so on. And there's also the fact that Alexander and I just like topology. In fact, when I was a student of mathematics, topology was actually my first love. Okay. So one thing you could say is, well, maybe this notion of dependence you talked about really should be more topological. So we have topological spaces. The open sets are possible measurements we could give for the values of a variable. And maybe dependence should just mean, say, y depends on x, if I can actually approximate the y values arbitrarily by restricting the x values. Right? That will be a topological take. So not my story of if the values are the same, the x values are the same and the y values are the same. No, it's about approximation. Actually, we do that. So in the paper, we also have a topological version of the whole setup. So we topologize the dependence models. We define things this way, which I'm not going to go into any details of, but that's possible. And the result is a logic LCD, which is still decidable. But, and actually, interestingly, the only difference with LFD is that the base operators now become S4. This you expect, because when you move to topology, you expect to go to S4 from S5. What's a bit more interesting is that an action like this is still valid. And if you think about this, I promise you, if you just take the time to think about this for a minute, you will actually see that this action expresses continuity in approximation. That's all I'll say. Of course, my philosophical students wouldn't like this because they also think topology is wrong since it has points in topological spaces. So what we really should be doing is point-free topology. There at the moment, Alexander and I are a sort of boundary because we think that's interesting, but we don't know exactly how we should define dependence in a point-free way, but this probably can be done. So that's what I wanted to say about advertising the topological viewpoint. So I'm going to end with two examples from the real world. I guess I still have 5 minutes. Yeah, okay.
With discussion.
Oh, with discussion. Well, then I go very fast.
6.
Okay. So we could go to various areas where dependence plays an important role. One of those areas is linear algebra. And in fact, one of the first logics that I know of dependence was actually inspired by linear algebra. It was in a JSL paper by Michiel van Lambalgen, I believe in 1993. That's a wonderful paper. Michiel actually gives an abstract logic, it's actually of independence. And he gives a number of principles. Some of them are like the ones we find in LFD, but transposed to the terminology of LFD, Michiel has one principle, which we typically don't have. So that's called the Steinitz exchange principle. Maybe I should say just a small word. Of course, in linear algebra, your notion of dependence is very different. So a vector depends on other vectors if it can be written as a linear combination. That is the definability viewpoint I mentioned at the beginning of my talk. So that's totally in harmony with what we do. I already had a slide about that. So that's not a big difference in itself. But for instance, the Steinitz exchange principle is because this is definitely not valid in my semantics, not valid. But it actually has a very trivial explanation in linear algebra. The antecedent says that Z can be written as a linear combination of the X and the Y. So it's sigma of lambda I for the X values plus mu times Y. Why do I have an or in the conclusion? For the following simple reason. There's only two cases. Case 1, mu equals 0. In that case, Z only depends on X. Right? Case 2, mu is not equal to 0. Then I can divide by mu, and then in fact I can write Y as a linear combination of the rest. That's all. That's the Steinitz exchange principle. Question. linear algebra is LFD plus at least this. And in Michiel's view, it seems to be about this. We'd like to have theorems which prove that. We'd like to understand this extended system, but at the moment, this is all I can say. I gave this example at my Stanford Logic seminar, however, in April. And one of my students, David Gonzalez, said, but look, Johan, you're too late. Because there is already a famous abstract analysis of dependence in linear algebra. It's called matroid theory. And then he said, and what's even worse is that the founder of matroid theory is Bartol van der Waarden, so a Dutchman. So you know nothing. You don't even know what your own countrymen have already done. Okay. Matroid theory is a different approach. It's actually an abstract analysis of independent subsets. However, after David said that, for his term paper, he proved the following, that each matroid, in the sense of matroid theory, can actually be represented as a dependence model in our style. So at the end, he came with good news. Okay, but again, lots of open problems. Let's see whether I can... Maybe I should leave a few minutes for questions. So this I'll just flash. The other concrete example of dependence and independence that is really worth looking at is actually games, to have something different from linear algebra. I don't think I should get into that. I'd be happy to talk about it if you ask me later at the conference about this. Games are full of talk about dependence and independence of moves and so on. That's also something discussed in by Hintika, etc. Basically, let me just say that if you look at imperfect information games in the start of our logic, you actually get a very different view of how games behave from the dependence logics that exist. And basically, gameplay has something to do with associating dependence models with games and then changing those dependence models as you make your move or choose your strategies in a system we call dynamic LFD. So I think I'm almost there. There's, of course, lots of further notions of dependence you could look at, which later. Of course, what I've told you relates to lots of things, so the paper is going to contain a number of comparisons with what other people have done, but I think I've said enough for now. So, in other words, the work that we're doing now is doing some extensions of the language just to see where the decidability breaks, but maybe the most exciting thing is go out into the world, look at particular areas, linear algebra, game theory, causality, and so on, and ask yourself, what do I recognize as exemplifying the common features of dependence and what's special for that area and which beautiful principles can be discovered, so to speak, on top of our base logic? Thank you very much. Thank you.